gas cycle. So that means we can assume ideal gas, right? And this one is the Otto cycle. So this is for spark ignition engine. So that's the closed system, right? So this is a closed system cycle, okay? And so let's work our way through everything. Within the Otto cycle, you have, starting at state 1, this is the fresh air and atmospheric pressure you're bringing in. And you have isentropic compression up to state 2, okay? 2 to 3, we have our constant volume heat addition. Okay, so this is where we're adding heat and the volume is constant, right? So there's no work. Then we have isentropic expansion, okay? And then we have our heat rejection at constant volume, okay? And this is when the exhaust valves open, we rush out and have all this exhaust energy that we lose out the tailpipe. We're modeling that as a heat rejection process at constant volume. All right, the TS diagram, we have these isentropic processes, so their entropy is going to be constant, right? So we're compressing at constant entropy, so our temperature and pressure go up. Then we're adding heat, so our entropy increases. It goes from left to right, right? And then we have isentropic expansion, so we're dropping, okay? And then we have our heat rejection, right? So we're going from right to left, or decreasing in entropy, okay? So here we have, the 1 to 2 is our work in, and 3 to 4 is our work out, right? Work in, work out, right? Couple parameters we have our compression ratio, which is because all the states are either at bottom dead center, 1, 4, 2, and 3, or at top dead center. So they're all at bottom dead center or top dead center, which the compression ratio just tells us about that volume ratio between those two. Okay. Mean effective pressure more just kind of normalizes the work. So this work net is what you have in this area right here, right? It's this mean effective pressure says, okay, what if we just changed the displacement from here to here? But what mean effective pressure would it be right here if we just had that displacement volume and had that same area of work net? What would that pressure be? And that normalizes whether you have a small engine or a big engine, because if you just increase displacement volume, all it does is make this area bigger here, and so forth. Okay. All right, from the calculation, we have a heat engine, right? Okay, where work net, desired output, required input, we have QN for our thermal efficiency. Or if we do conservation of energy around the whole cycle, right, you have QN, Q out, work in, or work net is work out minus work in, right? So then you can relate QN minus Q out equal to work net, right? And that's what's kind of done here, right? This is also this 1 over is QN over QN, right? All right, so if we do the COE, so it's closed system COE. For each individual process, we're neglecting kinetic and potential over here, right? We have the same mass because it's a closed system, so the same mass is at 1, at 2, 3, 4, right? It's all the same mass, right? So if we divide out mass, we have Q minus W equals delta U. So for any process in the Otto cycle, you have either heat or work, right? Isentropic, we have no heat, right? Heat addition, constant volume heat addition, there's no volume change, so we just have heat. In isentropic, no heat, constant volume, so no work, right? So we have this. If we do it for heat in and heat out, we get this. We also have isentropic relationships for an ideal gas, right? Right, for process 1 to 2 and 3 to 4, they're isentropic processes, so we can use those relationships for that, right? 2 to 3 and 4 to 1 are not isentropic processes, but we can do it here and here. Okay. Diesel cycle, still a closed system, right? It's an ideal gas, right? The big change is how we're adding heat, right? We still have isentropic compression, okay? In the Otto cycle, we instead went from 2 to 3 up here, and we had 3 where we added constant volume heat addition, right? But in this one, diesel cycle, it's constant pressure, so we're going over here to state 3. We're at constant pressure, we're adding heat, okay? So again, this is compression, so it's working. All right, 3 to 4 is isentropic expansion, okay? So that's our workout. And then 4 to 1 constant volume heat rejection, okay? But the other thing that happens from 2 to 3, because we're changing volume, right? We're going from 2 to 3 here. We have work, right? So this process also has a work out. Okay, where in the Otto cycle, it did not because it was at constant volume. Okay. So if we do the TS diagram, isentropic compression, constant pressure heat addition just changes that slope, right? Constant volume would have been here. Constant pressure just changes that slope on that heat addition, going left to right, adding entropy, decreasing entropy down here, so going right to left. Okay. Work in, work out, heat in, but we also have work out here. Okay. Work in here. Heat is easier to see. Heat transfer is easier to see on the TS diagram. Work is easier to see on the PV diagram, right? All right. So for that heat addition process, since it's closed system COE, so we have our closed system COE. For that heat addition, we have that work term also and the heat, right? But because the work is at constant pressure, the integral of PdV is P times delta V. Pressure we can take out of the integral. We can combine these two terms, the change in internal energy in P delta V, and we get change in enthalpy, or Cp delta T. Okay. Heat out is still the same as we had in the Otto cycle. It's at constant volume, so you just have heat transfer. Okay. So the thermal efficiency, still work net over Qin, 1 minus Q out over Qin. The other parameter we have the compression ratio, but we have a new one also. We have this cutoff ratio, right? The compression ratio tells us about this volume change. Okay, large volume, small volume. But now we have state 3 here is at a different volume. So the cutoff ratio tells us about that change, that new location we have. Okay. We still have 1 to 2 and 3 to 4. We still have isentropic relationships, right? In the diesel cycle. Okay. If we change to the Brayton cycle now, this is still ideal gas, but it's an open system. So each component is an open system, right? So when we draw our boundary around any of the components, we have mass flow rate coming in and out, right? It's not the same mass, so it's not a closed system. It's a mass flow rate entering and exiting. Okay, so we have an open system. That means we have open system conservation of energy. All right, so this is for gas turbines, right? So if we start our way through, we have our isentropic compressor. Okay, 1 and 2. We have our constant pressure heat addition. Okay, we're going through our heat exchanger, flowing fluid, and we're adding heat. Okay. All right, so we're going from left to right. We have our turbine, we're expanding, so we're dropping pressure and temperature isentropically to 4. Okay, and then we have our heat rejection, so we're going from right to left. Okay. All right, so when we look at the analysis, we have what's here is from the open system COE, right? So if we did the COE open system, every component, when we do the analysis, is one inlet, one outlet. All right, steady state, neglect kinetic and potential. All right, then we just are left with heat transfer, work, mass flow rate in and out. So mass flow rate in, mass flow rate out on each component. And then if we divide, since conservation mass, same mass flow rate in and out. So that means we can pull the mass flow rate out and divide it out. This is what we get then, right? So this comes from the open system COE. All right, so if we do this on heat in and the heat out component, or heat exchanger, we get these two equations, right? We have thermal efficiency, so it's still work net over Q in, or 1 minus Q out over Q in. Okay. We have isentropic compression and expansion, so we have these equations. We're dealing with the pressures, right, instead of volumes here, because that's what we're set up with, right? If we look at the cycle, you have two pressures, right? The compressor's changing the pressure, and the turbine changes the pressure. So we have one pressure down here, a low pressure, and a high pressure up there of 2, 3. Okay, low pressure 4 to 1. So we have a pressure ratio that defines that, right? So that's also equal to just P3 over P4, since pressure 1 is equal to 4, 2 is equal to 3. Okay, so compression ratio for a closed system, open system, we have this pressure ratio. We can also add a little bit of accuracy to our cycle problems for Brayton and put in isentropic efficiencies. All right, so over here, we would have the actual for A here and for S. And over here, we would have the actual 2, right? And this would be 2S. All right, so now if we add some complexity to our cycle, basically trying to increase efficiency, we have here is a Brayton cycle, but with a regenerator, okay? So we're adding just one more component to this, right? So we still have compression work, we're putting work in. We still have the turbine where they're getting work out, and work net is equal to work out minus work in, right? So if we look at our TS diagram, here's our work in, here's our work out. So that doesn't change with the regenerator, right? We could remove the regenerator and still put external heat, take us all the way from 2, all the way to 3, and reject heat from 4 all the way to 1. And we would have a cycle without a regenerator. But with it, the work is still the same, all right, because we're not changing points 1 and 2 and points 2 and 3. What we're doing is decreasing the external amount of heat that we have to add and the amount of heat we have to reject. So we're just moving thermal energy, kind of preheating before it gets to the combustion chamber with thermal energy we have that would normally get exhausted to the atmosphere. Okay. So that means the only external heat transfers from 5 to 3, and the heat rejection is from 6 to 1 now. Okay, so we're now, instead of rejecting heat all the way from 4 to 1, we're only taking and rejecting heat to the outside from 6 to 1. 4 to 6, we're moving internally that thermal energy right here. So it's heat transfer here, but it's still internally, right, to our cycle. And we're moving it to heat and preheat, right? So what happens is we can define an effectiveness for this. If it was a perfect regenerator, 100% effectiveness, we would be able to take state 2 here coming in and heat it all the way up to the same temperature we have on this side, right? This is our T4, this is our T2 coming in. We would get T2 all the way up to that T4 temperature in a perfect regenerator. So that's our max, is that basically getting 2 all the way up to this point here, which is 4, right? So the same temperature right there, okay? But
question.
yeah.
So had we made this cycle without the combustion chamber, would this be a closed system or would it still be an open system?
Still be an open system. So it's still, mass flow rate is still flowing in and out of our devices, okay? I mean, if you put your boundary around everything, right, you can analyze this cycle as a closed system. But I'm talking about when you look at an individual device component, then we have mass. If you have mass flowing in or out, it's an open system.
Okay. And then had we added like other components, would this still be considered a Brayton cycle?
Yeah.
I feel like sometimes we add some stuff and take away, and that kind of changes which cycle we're actually looking at.
It's still a Brayton cycle, right? So most of this we're still adding to it, right? And you'll see it on the next slides. We're never removing. So it all has the. I'm gonna go back one slide for me. Apparently not. My computer's stuck. All right. So they all have compressor, heat exchanger, turbine, heat exchanger. So we still have the compressor, heat exchanger for heat in, turbine, and they're not showing it because they're just running out of space as it gets more and more components. They don't show it. You're exhausting to the atmosphere here with hot and bringing in fresh. So this is your heat exchanger. It's basically a heat exchanger. We're rejecting heat. So we have those for the Brayton cycle. We have those 4 components, right? So that's what defines the Brayton cycle. We've added a component, regenerator. So it's still a Brayton cycle, but it's with regeneration.
Okay.
All right, so the effectiveness basically tells us about, when we have our max that I mentioned, is this difference, right? If it was a perfectly effective regenerator, like a really good heat exchanger, like infinitely large, we would be able to get all that, raise that temperature 2 all the way to 4. But in reality, things don't get all the way up there. We can't make an infinitely large heat exchanger, so we get to some value below it, right? So that's this 5 minus 2, so the actual. The other thing to think about, if we were adding heat externally, we would go from 2 all the way to 3, right? So that would be the Q in of a normal Brayton cycle, would be the Q in from, let's say Q in old is Q from 2, say 2 to 3. But with a regen, so that's Q in with a regenerator, that would be Q in from 5 to 3, okay, which is really just the Q in So Qn new is equal to the Qn old. I'm running out of space here. Minus this Q regen. So this new amount of Qn we have to put in here when we add a regenerator is just this. Right? It's subtracted off this amount. Okay? Because then if you didn't have a regenerator, we would have to go that full amount to heat it up. Okay. Now, I know you guys wanted more complexity, so we have more complexity here, right? So we have, in this case, still a Brayton cycle. Okay, so we still have compressor, turbine, combustion chamber, and our heat rejection process for an ideal gas. Okay, it's an open system cycle. Okay, but now, yeah, go ahead.
So are we always assuming that the gas entering this is superheated or a saturated vapor?
Neither. It's an ideal gas.
Okay.
Yeah. So in the Brayton cycle, it's all ideal gas. So we have, it's air operating as an ideal gas. Okay. So it has the ideal gas law and ideal gas relationships. Okay. It's just an open system. Okay. And each component has mass flow rate entering and leaving. Right. Okay. So if we work our way through this cycle, we have our compression. So isentropic compression. Now we have an intercooler. So we're going to reject some heat here. So then we go from right to left. Okay. So we're rejecting heat. So that takes us to state 3, and we compress it again. Okay. To 4. We have a regenerator, so that's kind of our preheater there, to get us to 5 at constant pressure. So we're adding thermal energy, so we go from 2 to 4. Now we hit our combustion chamber, so we have Qn, and that's from 4 to 5, going from left to right, adding entropy. We expand, so we go through our turbine from 6 to 7, okay, and we have our reheater, so we add some more heat in, okay. So by adding heat in, we go from left to right at constant pressure, and then we go through our turbine and expand again, and then we have our regenerator, which moves that thermal energy to another part of the cycle. Okay. And then we have our heat rejection process Q out there. Okay. So here we have work in, let's call that 1. We have work in 2. We have work out 1, work out 2. Okay. So if we wanted to figure out work net, that would be work out 1 plus work out 2 minus work in 1 minus work in 2, because we have 2 turbines, 2 compressors, right? Or if we did our boundary around the whole cycle, we can relate it to heat transfers. We have 2 heat ins, right? And then we have 2 heat outs. We have the intercooler and we have the exhaust, right? Okay. If we only did this with one, if we did just a normal Brayton cycle and didn't have a regenerator or intercooler or second compressor or second turbine, we would have just went from 1 to 2 up, right? Added heat completely from the combustion chamber and had 1 turbine to drop us down. We would have had this amount of work net, right? That's our work net. By having that intercooler in second compression, we added this amount of work net, right? And then by adding that reheater in the second turbine, we added this amount of work net. So we've just added that area and this area to the original Brayton cycle by putting in the intercooling and reheating and regeneration. Okay. All right, so this switches to chapter 10. So now we still have open system, but we're using that phase change. So now we're utilizing the phase change, and the components are an open system, right? So it's still kind of doing the same thing that the Brayton cycle is that had an ideal gas, but we're changing it because we have the vapor dome now, right? Because we're utilizing phase change. So we have a pump from 1 to 2 where we raise pressure because we're in the liquid region right here. And then we're in the boiler, constant pressure. So we're adding heat, right? We're staying along the pressure line, okay? But we're adding heat, right? So we go from left to right, add entropy. We got the dome, right, with the phase change in the middle, okay? And then at 3, we isentropically expand in the turbine and end up at 4, right? And now we have our heat rejection process, which occurs in the condenser because we're condensing the fluid out, going to a saturated liquid. Remember, we have a quality of 0 here at the inlet to a pump, right? So we have work in, we got work out. We have our heat in here, heat out. Okay, it's still open system, one inlet, one outlet. When we do the conservation energy, we get just heater work for each of the devices, right? So for the pump, it's just change in enthalpy. Boiler, no work. Heat's just change in enthalpy. Turbine, change in enthalpy. Condenser, change in enthalpy, right? So work net is either Q in minus Q out or turbine work minus pump work, right? Still the same thermal efficiency equation because it's a heat engine. Okay, it's a power cycle. Okay. Right, so then we also have the steady flow reversible work we can use for the pump, right? So that comes from this integral equation for steady flow reversible work. And for the pump, we can assume the water is incompressible, so this from 1 to 2, so specific volume can go out, and we take the specific volume out and integrate, and you get V delta P. We can't do this, even though it's reversible from 3 to 4 for the turbine. We can't do this for the turbine, so that's why you don't see it, because the volume, specific volume changes a lot to the turbine. Okay, so we would have to know how that specific volume is changing to use this equation. Okay. So that's where we just use the enthalpy one. But for the pump, it's useful because we don't have many properties for state 2. So we can set these two equations equal and get a relationship to get us enthalpy at state 2. We can get a little bit more accuracy to the actual cycle from the idealized by adding the isentropic processes and isentropic efficiencies for a pump and turbine. Okay. Right. For the pump, we also can do the the steady flow reversible work equation for the isentropic version. Okay. Okay, if it's an isentropic pump, and this is 1, and this is equal to this. So we can utilize this. The difference is we have, say, water in this case, so we got to use our states and our property tables, right, to get enthalpy at 1. We could then use 1. We know H2S is isentropic from 1, so we could utilize that information to then, if we were given isentropic efficiencies, then we could utilize the equation to solve for 2 actual, right? Or same with the pump or the turbine. Given isentropic efficiencies, utilize state 3 information. Knowing it's isentropic, we can get 4S, and then utilizing this equation, we can get our 4 actual. Now we add components, right? So this is the simplest change, is a reheat, okay? And that's a pump. We still have a boiler, still have a turbine, still have a condenser, but instead we're expanding a little bit, and then we reheat it, okay? So we have heat in here, but then we have heat in through the reheater, right? Pump has work in, the turbine has work out. Okay, we have, if you want to separate it, you have work out low pressure and work out on the high pressure, okay? And heat out from our condenser. Okay, so heat in, we have a primary and a reheat section. Work out has each of the turbines, right? But work net would have this work of the turbine out, which is these two, minus this pump work in, right? Down here. When we look at the diagram, we still have that isentropic compression. We're adding heat, okay, in the boiler. Then we go through our first turbine and expand to 4 isentropically, but now we've reheated, okay, so we're adding heat again. And then we expand again, and we get our work out here, okay, and work out here. Okay, heat out in the condenser, and work in from the pump, right? All right, so with this one, you know, we're reheating because if we didn't, we would have gone, if we had just one turbine and no reheater, we would go down all the way to here, right? So that has 2 things. We would have a quality that's pretty low, and that turbine might not handle it in later stages, eroding the blades, okay? So that would have a high quality that's not good for that. But also, by reheating it, we've added this net work right here, okay? That area gives us that much more work out of this cycle. We have feed water heaters. Okay, so in this case is the open feed water heater. So it is basically, you know, reheating or heating up that feed water that's feeding the boiler, okay? But it's basically a mixing chamber is really. They're calling it an open feed water heater because that's the feed water is what's going into the boiler and it's heating it, okay? It's warming it up. So if we look at this cycle, we still have pump, boiler, turbine, condenser. We're just adding this kind of section in the middle here, right? So if we work our way, we have 1, right? It's a quality of 0 here because it's inlet to a pump. We isentropically compress. We get to this pressure that's at the feed water heater. Okay, and then we mix basically in the feed water heater. So that means 2 and 6 are mixing to get 3, right? So 6 is here. We'll get to that in a second. It mixes with 2 and gets us 3. Okay. Well, 3 is an inlet to a pump, right? So it has to be at our quality of 0. Okay. Again. Now we pump it again to raise its pressure up to the boiler pressure. Okay, so we get to 4. We add our heat in. So that takes us to 5. Okay. 5, we expand through the turbine. So as we go through, we isentropically expand all the way to 7, right? And then we have our condenser. Condenses the fluid back to 1, right? But it's somewhere in between. So in this case, in 6, we're pulling off some of that steam, and that's what's going into our feed water heater that mixes with 2. So 6 and 2 mix to get 3. So the part that challenges us and that we saw in the examples we did is it's not one inlet, one outlet for every component, right? We have the turbine splitting up the mass because we're pulling some off here, right? And then the rest ends up at the condenser. And then the feed water heater brings the mass back together, right? So we have this full mass going through here. So through the heat in, we just use delta enthalpy, right? But Q out has a fraction of that original mass is gone, right? So if this is the full mass here of 1 fraction, this being y fraction, then 1 minus y is left over here. Okay, so that's the fraction we would have times our enthalpy going through. The turbine out, we have the full fraction working from 5 to 6 because the full mass is there, it doesn't leave until 6. But then from 6 to 7, you have only 1 minus y of mass going through, okay, of the original. Okay, so that's what's going on that enthalpy. And then the pump in, we have 1 minus y on this pump, and then the full mass on this pump. Okay. With the closed feed water heater, these are basically heat exchangers. Okay, we're still trying to preheat and heat up that feed water, right? So in this case, though, they're not touching. It's not a mixing, right? This is a single pipe, and this flows through to get to 3. Okay, so they don't ever contact each other. So that means they're at different pressures. Okay, they don't have to be at the same pressure. They have different pressures now. All right, so when we work our way around, we get 1 inlet to a pump. But the big thing in this diagram you see is this 1 raises it to pressure 2. Pressure 2 is at the same as this pressure, which is a mixing chamber, which means they're all at the same pressure in the mixing chamber. So they're at 5's pressure. That's the max pressure. So that's all along that max pressure. So we went all the way up to that max pressure with pump 1. Okay. Now what we have in this closed feed water heater is 2 is getting, that's preheated, and 9 will get up to that Tsat of this pressure, right? So this fluid from 7 to 3 is what's preheating this feed water right here, and it can get up to that max of that temperature because this is what's heating it up. Okay, so it can only get up to this temperature right here, and that's what you see at 9. Okay. In this diagram, it's a mixing chamber. So 9 and 4 mixed to give us 5. Okay. So we have 9 and 4 mixing to give us 5. So 5 better be in between the 2 inlets. Right. All right. So then we take 5 and we add heat in our boiler. Okay. We expand through our turbine. Isentropically, we have our heat rejection process and our condenser. But now when we go and we pull through this mass off of the turbine to go through the closed feed water heater, we end up at 3 right here when we go through it. And now we have to, we can either go to the left or drop its pressure and go to the right. So in this diagram, it's increasing its pressure. It's going to the left. So because we're at this pressure right now, we're at this point at 3. So we would raise its pressure in the pump. So that would get us, again, this is quality of 0, inlet to a pump. We go all the way up to 4, isentropically, and then 4 and 9 mixed to give us 5, right? Well, we could also, and we saw this in the example that we did, drop its pressure at 3, right? We had the example where we had a trap, right? Kind of has a valve, and that was put into the condenser, and that would be like an isenthalpic process where you would bring basically that fluid down to the low pressure of the condenser. So when you get out of this closed feed water heater, you got to either go drop its pressure or increase its pressure to connect somewhere. You still have the full mass coming through here, a fraction y coming off there, and the 1 minus y going to the condenser, right? Until they come together again. In this problem, they're coming together in the mixing chamber, you know, and you see all the mass flow rates also in the closed feed water heater. I'm not going to have, I don't think, one of these on the test, but this is basically a Brayton cycle on top of a Rankine cycle. These, you get the higher efficiency than having just a Brayton cycle or just a Rankine cycle by itself. Okay, you end up, you know, you can get efficiencies in the 50 to 60% range. I'm not sure exactly where they are in current technology on this, but you overall can get more efficient out of having this. Okay, and that's because you can run a little hotter temperatures in the Brayton cycle, right? Because you're running air through it. So with high air to fuel ratios, you can run some hotter temperatures into your gas turbine than you can into a steam turbine, because gas doesn't transfer heat as easy as, say, the vapor here to the blades. So you get a higher temperature through your gas turbine, okay? And then use that, normally what you would reject to the atmosphere, use some of it to go to a steam cycle, and then you reject some heat over here. Okay. All right, so now this is switching. Oh, yes.
Sorry. You
Sure.
said that last slide that will not, we don't have to worry about that for the exam.
No, I won't have one on the exam.
Okay, thanks.
Mm-hmm. We have here, we're switching now to refrigeration cycle, okay? In this case now, all these diagrams are going counterclockwise, right? So because we're putting in a net amount of work in, right? So they're going counterclockwise. Everything in these heat engines, they're going clockwise because we're getting a net work out, right? So now we're going counterclockwise, okay? All right, so in our refrigeration cycle, right? So that was our circle when we were back in chapter 6, where we did R or we did HP for a heat pump, right? That was what, this is now what's inside that circle, right? If we work our way around the diagram, starting at 1, we're a saturated vapor going into a compressor, and we compress it up to 2, okay, isentropically here. We have our heat rejection process, so we go from 2 to 3. So that means we're going from 2 to 3 and condensing that fluid. For this to go into the heat to go into the warm environment means the fluid going through the condensers at a higher temperature than the warm environment. So at least 20 degrees higher we're here than this TH of this warm environment. So the fluid is at a hotter temperature, so we can have heat go from high to low. Right? Then we get to the saturated liquid, right? After the condenser, before the expansion valve. Then we take it through an expansion valve where we have delta H is 0, our isenthalpic process, right? And if we had a turbine, we could take it down to here, right? And we would have some work out that we'd get, so then we wouldn't have to put in as much work in from the compressor or network in. But we can't get a turbine to work very well. It's not very practical to get a turbine to work with all that liquid, okay? So instead we send it through an expansion valve, which is a simple component, not very expensive, and that takes us to 4. Drops its pressure, which drops its temperature significantly. and now we have our heat addition process. We evaporate that fluid. Okay, so that means to get heat from this cold refrigerated space of TL, that means inside the evaporator, the refrigerant is at a lower temperature than TL, right? At least 20 degrees Celsius lower to get that heat transfer, right? So then we can have heat go from this being the higher temperature to the lower temperature of what that refrigerant is, okay? So all that magic that's happening in the refrigeration cycle is all about changing the refrigerant's pressure and temperature, okay? So we can get heat transfer going in the direction we want it to, right? And since we're moving overall, if we look at our full cycle, we're moving heat from a low to a high environment, we're putting in work, right? So if we use this as a refrigerator, we want QL as large as possible, so that's our desired output. If we use it as a heat pump, we want QH as large as possible, so that's our desired output. And each component is one inlet, one outlet, and it's an open system. There's phase change. All right, so one inlet, one outlet, open system conservation energy reduces to just change in enthalpy for each component, except for the expansion valve, which is just zero change in enthalpy because there's no heat or work. All right, so the cascade, it's basically just one vapor compression cycle on top of the other. Okay, we have one right here, and then we have another right here. Okay. And we're just have a heat exchanger in between that relates the mass flow rates to the upper A and B cycle, okay? And that's what you see right here from conservation energy on that heat exchanger, which is the evaporator on one side, the condenser on the other, okay? So by doing this, we just are sending, we have isentropic compression, we have our heat rejection, so we're condensing the fluid to 3, isenthalpic process through the expansion valve, heat addition through our evaporator, evaporating the fluid. Okay, so we have the lower vapor compression cycle. But then, starting off again to the inlets of the compressor, so we can have state 5 right here. Isentropic compress, condense, isenthalpic process, and then our evaporator. And we have our area right here, right? If we were trying to do this with one cycle, so if we were just using 1, 2, 3, and 4, just one compressor, condenser, expansion valve, evaporator, we would have had to go all the way up here, all to 7, and then 7 would have had to go all the way down here. So we would have had a decrease in the refrigeration capacity and more compressor work we would have had to do in. The other thing, the benefit you get is you can do two different refrigerants, right? A refrigerant to this upper and the lower because they don't ever touch. They just have heat transferring between the two. Okay. Next one. All right, we did an example with the flash chamber, right? So it's kind of, in the diagram, looks similar to what you saw for the cascade system, but you're just using one refrigerant. You have this flash chamber, right, that's separating the vapor out here and the liquid down. So that means basically from that quality you have at 6 is the mass flow rate at 3/6. And then the liquid 1 minus x6 is the mass flow rate at 7, which is the liquid, because that's the remainder, is liquid, over 6. Okay. So when we work through, we have compressor to 2, okay. Here is a mixing chamber, so that means 3 and 2 give us 7. They mix and the outlets are 9. So the mixture mixes and gives us 9, somewhere in between. And then we compress again to 4 isentropically. So then we have our heat rejection to 5, isenthalpic process to 6. And this is where we're splitting the vapor and the liquid, right? And then we, our expansion valve with constant enthalpy again, and then our evaporating, right? Going from 8 to 9, we're evaporating. So we have our QL, QH. Okay. So the magic and the understanding is that flash chamber to do this cycle. Gas refrigeration cycle. So all this is the Brayton cycle, okay? Because it's got a compressor, turbine, and 2 heat exchangers. We just reversed the direction, okay? When we did the Brayton cycle in chapter 9, it was this diagram here, but it was clockwise. So the processes were going in the clockwise direction, okay? To make it go counterclockwise, that means we're compressing over here on the right now because we're raising its pressure and temperature. We're rejecting heat. We're going from right to left. So we're rejecting heat now. In that warm environment, we're expanding, lower pressure and temperature through the turbine, and then we're adding heat to go back to 4 to 1. Okay. So coefficient of performance, you have your QL, work net in, we have compressor work in, and you have turbine work out. But you're going to have to put in more work in on the compressor than you're getting out from the turbine. So you get a net work in. Okay. All these again are one inlet, one outlet. Okay. That's all I have. Do you have questions for me? For the different cycles or understanding? Okay. Well, then that's it for today. Please don't hesitate to email me or have a time, email me to meet up to have questions about any of this material so we can go through it and make sure you understand it, okay? And that's it for today. All right, so then on Friday, I'm hoping again to send that email to give you a little bit more details about the exam, and then the exam's on Monday, all right? Have a good rest of your week.
Bye, Dr. N.
Bye.